Okay, so now what we're interested in is power in the alternating current circuits. So this is power in AC circuits. Pretty straightforward calculation right here. It kind of turns into plug and chug most of the time. We remind ourselves that the power equation from before is I squared times R. That was our power equation when we were first dealing with circuits. But now I've got to replace this with the alternating current equation, okay? So we remind ourselves that the alternating current equation was capital I for the amplitude of the current, sine of omega dt minus phi, and we're going to be squaring that, and then we're going to multiply that by R. So this right here in the squared, that's my alternating current that we found at the beginning of the chapter. Let's manipulate this thing a little bit to make it look nicer, and we're going to have I squared R. So I brought the R forward inside here. I is still squared from up top. Sine squared of omega dt minus phi. Okay, now we're going to do a little bit of hand waving right here, okay? We're going to talk about the average power over some period of time, okay? If you think about the sine function has an average of 0. There's just as much above the x-axis as below the axis if you go for some period of time. However, the sine squared function kind of has those peaks. Take a look at your book if you can't remember what that looks like. But the sine squared function looks like this. The average of the sine squared function over some period of time is 1/2. So what that means is we can replace this whole thing right here over a period of time. If we try to find the power over a period of time, we can replace that whole thing with 1/2. So we have that the power average is equal to I squared over 2 times R. So the I squared stays the same. I'm trying desperately not to sneeze it. Woo. I promise I'm not sick. It's allergies. See, in a way, it's kind of like I'm teaching right back in the classroom. Okay, in all seriousness, they told us to keep the classroom teaching as consistent as possible to what we usually do. So you guys know that I have sneezing fits all the time. That's fine. But then you also know that I drink a lot of coffee, so I'm going off camera right now to have a sip of coffee. We're doing it live, folks. I can't really have an editor. And you guys know I'm going to end up sneezing again. That's okay. Okie dokie. I think I got myself recovered here. Okay, sorry about that, guys. All right. Now again, we're finding the power average over some period of time. Because I'm doing an average amount of time, I can replace this sine squared with 1/2, and now we've got that down there. We're going to write this in a very unique way, okay? We're going to write this as I over the square root of 2 squared times R. So I haven't done anything here. All I've done is I've said the denominator is going to be the square root of 2. If I square both the numerator and the denominator, I'm going to get back I squared over 2. This kind of feels like a duh, why are you doing this moment. The reason we're doing this is because we wanted to find a new term. We wanted to find the current root mean square. So this right here, IRMS, is the current root mean square, okay? Root mean square is equal to the amplitude of the current divided by the square root of 2. This allows me to rewrite the power equation. The power equation average is now equal to I RMS, the quantity squared, multiplied by R. So what I've done is I've replaced this guy, I over the square root of 2, with IRMS, and now I have IRMS squared. squared multiplied by R. We can do the exact same thing for the voltage, and we can replace the voltage RMS. So VRMS is equal to the voltage divided by the square root of 2. Or we can do the same thing if we're talking about an EMF, and we can have root mean squared is equal to E over square root of 2. So we've got these root mean squared terms, and the question is, what exactly are they doing? I'm going to go on to the next whiteboard and explain what that is. Make sure you have this in your notes. Dramatic pause. Okay. Now the question is, what exactly does that stuff do? When they tell you that your household voltage is 120 volts, what they are referring to is the RMS. So when they tell you household voltage is 120 volts, this is VRMS. Okay? So that's not the actual voltage that's coming out of your wall. It can actually have a maximum output if I throw this into the equation. So VRMS is equal to V over the square root of 2. So that means 120 is equal to V over the square root of 2. And you can think of this voltage as the maximum amount of voltage. And if you do that math, you're actually going to see that the maximum amount of voltage is 170 volts. So the wall outlet is actually providing 170 volts. You didn't realize that because we always say it's 120 volts, but what that's referring to is the average amount, based on the average amount of power, that's how much voltage is coming out of the wall. The maximum amount of voltage is 170. This is a typical AP problem, and it's probably a problem I'm going to give you on the quiz this week, is figuring out the maximum amount of voltage, okay? Finally, we have our last power equation, but I don't think I've ever actually used it. The power average is equal to the root mean squared of the EMF, the root mean squared of the current, multiplied by the cosine of phi. And this cosine of phi is referred to as the power factor. I don't think you guys really need to worry too much about that. Just read up in your book a little bit on that. But that's how we handle all that stuff. So we went over power in AC circuits. I sneezed quite a bit. We used 1/2 because we're figuring out the power over some period of time. And then we got our current root mean square, our voltage root mean square, and I explained what those root mean squares are. You should understand how to calculate the maximum amount of voltage or current if I give you the root mean square, current, or voltage. Hint, hint, wink, wink, nudge, nudge.